In all flows which involve mass action, it is not the dynamic viscosity mu which is significant, but its ratio to the density rho, called the kinematic viscosity nu. Viscous fluids of different densities flow under gravity through small passages such as these at speeds inversely proportional to their kinematic viscosity. The dynamic viscosity of mercury is greater than that of water, but its kinematic viscosity is evidently smaller. A heavy gas, however, having a dynamic viscosity much smaller than water, has a much greater kinematic viscosity, and hence flows far more slowly. In Poiseuille flow through uniform tubes, the velocity distribution is parabolic, just as in the case of plain Poiseuille flow. The resistance which it encounters is likewise independent of the fluid density because of the lack of acceleration in the zone of uniformity. At the inlet of such a tube from a reservoir, however, not only does acceleration occur, but the parabolic velocity profile develops only with distance downstream. For the same glycerin solution at higher speed, the development of the profile is appreciably less rapid than it was at lower speed. While for fast-moving water, the parabola is seen to develop extremely slowly. Such flows evidently do involve inertial effects, and hence depend upon the Reynolds number. In fact, the relative distance from the inlet required to establish the parabolic velocity distribution increases directly with the Reynolds number itself. Much the same situation is found in flow past an immersed body. When the liquid is a glycerin solution and the speed is low, the zone of appreciable fluid deformation is quite large. As the speed is increased, the deformation zone is more closely restricted to the vicinity of the body. When the glycerin is replaced by water, the zone becomes still narrower, and at sufficiently high Reynolds numbers, it is aptly called a boundary layer.